Good afternoon, Professor.
Good afternoon. Now that was Amy. That I know. Good afternoon. Thank you. Good afternoon.
Good afternoon.
Good afternoon, Caroline. That was totally Caroline. Good afternoon. That may be my favorite feature of life. Okay. Amanda. Good afternoon, Caroline. Good afternoon. Oh, sorry. And now I'm going to the chat. See, it's so funny how, how I cannot stay on the subject even when it hasn't started yet. I haven't even started the subject and I'm already on. But can I just point out that, I really, really believe everything I say, that it should not be a competition, it should be a collaboration. And I really mean that from the bottom. And yet, I think I create tacit competitions over the dumbest things, like hellos. That is not my intention. But okay, so good afternoon, Amanda. Good afternoon, Caroline. Good afternoon, Caitlin. That's visual. Good afternoon, Kevin Lynn. Ooh, another. Oh, see, he's so seasonal with his. Okay, good afternoon, Shamil. Now I'm going to the chat. Good afternoon, Amanda. Good afternoon, Kevin. Hi, Christina. Oh, and I will say, as long as I'm fostering competitions where they don't belong, I know Christina's been waiting in the waiting room since 1969. I'm like an orthodontist or something. I should have Highlights magazine out in the way. Okay, good afternoon. So thank you for being so early. Okay, good afternoon, David Kahn. Good afternoon, Felicia. And I don't really mean 1960. Okay, good afternoon, Caitlin. Hey, good afternoon, David. If that's actually your birthday, David, I want to know because it's very similar to mine. And also it means you're a Scorpio, close to the cusp of Sagittarius. Good afternoon, Amy. Good afternoon, Chloe. Good afternoon, Shamil. Someone else is in the waiting room. Give them a Highlights magazine. Okay. Good afternoon, Ashley. Wait, Ashley, I didn't even, you spell your name that way? Wait, I feel like that's a different, okay. Anyway, all right. I really should get, obviously I'm stalling. Are we going to Sophia? Whoa, Caitlin, is that, oh, that's like someone walking in front. I thought she was doing she was like, it's disco physics with a strobe light. Yes. Okay. Okay. Oh, now I got a new level. All right, Amanda just got points because she's actually hiding a laugh, which is the highest level of laughing. Okay. We have to get to business. I know. I'm just yeah, we have to get to business. So here's the business. Oh yeah, that is your birthday. No way. Oh, sorry. Oh, I think you could check. Let me know, by the way, folks. Sorry, all right, I'm sort of talking to a direct type person with that. Okay, very interesting. Happy in advance. Mine's very similar. No wonder you're so smart. Y'all tell me if you can't. I think you can change your names. I think you have that. Well, anyway, all right. So here's the story. The story is this. The story is that, as I hope is clear, and I want to start getting less. Oh, the story's that my board stopped again. I don't know what's been going on the board. All right, I'll start that again. But here's the story is, as I think as I hope is clear. Well, let me even say that if any details at all that ever are unclear to any of you about the exam or any other exam, I think the details are all in Google Classroom. I think when in doubt, you should text me, honestly, or email, but I think text will get an even faster response. I think the way we do on exams in physics is a little bit unusual, but it's the same way every single time. The way this exam goes will be the same format and structure as the final exam, as will be the midterm exam and final exam in Physics 204. Just okay. So the main thing to know, and that's what we're going to talk about for the next 2 days, is the material, the substance, the physics of this exam. Okay, like a review, you want to call it review periods, whatever. I hope it is clear. Well, we're going to find out in a minute. I hope that everybody has at least in their possession a practice exam that they are working on in their own private possession. We'll find that out in a minute, but I know no one's turned it in yet, and that's correct. You are not supposed to turn it in. It is for practice, but I hope everybody got it. I hope everybody's clear. I'm going to change the board. I hope everybody's clear that the actual midterm exam will be posted this Thursday evening. No later than 8 p.m., possibly earlier, but no later than 8 p.m. You'll have till Monday to do it. I hope that's all clear. I hope, again, if there's any questions, any doubt in your mind, especially if at any moment, any of you has a question of what constitutes cheating or what doesn't, if there's any doubt, you ask or text me or whatever. Because the overall thing on that, well, wait, hold on. I'm just looking at you. Okay. But I hope it is clear that the exam is posted, will be posted this Thursday. It'll be very, very similar to, but not identical to, the practice exam that we have now. Any differences will not, nothing is meant to trick you, but it is all meant to make sure that you understand the trickiness of physics. Today we're going to get some answers. Most of today we're going to get like answers or solutions or models for partial solutions for the practice exam, which really ultimately means for the real exam. Anything that you get a direct explicit solution for today and Wednesday, it means I'll like change numbers and change details to keep you alert for the actual exam. Anything, and I will be posting some things too between now and Wednesday. I'll post things online like solutions. Okay, anything that you get an actual solution to, you're of course welcome to use. That's the point. But you should look out for the fact that subtle details will be changed for the actual exam to make sure you're paying attention and learning and not just copying. Anything that I never give you a solution to at all, and there will be some things on this exam that I don't get to answer today or Wednesday, or I don't say anything about. The trade-off of that, if like part 4 or a problem 4 or something, I don't go over at all, I'll probably remind you of that fact, or I'll probably like admit it. But if I don't go over something at all, that means that thing is showing up on the exam exactly as is. It just means you've had that much more time to try to prepare for it and get answers from one another, et cetera, et cetera. Okay, I hope that's clear. Okay, I'm talking a little fast. I'm putting the board back on. I'm trying to put the board back on. But so again, today, mostly, we're going to be going over things in the practice exam, and Wednesday, same thing. That means for real, at any given, if anybody who has worked on this practice exam at all should be rewarded for their efforts. Like if you've tried to study and started looking at the practice exam and you have concerns or issues, you should definitely put them in the chat today and or text me. We'll probably put them in the chat, private or public. Whether or not I get to them immediately, like right away today, at least I'll know that that's a concern. And then if I don't get to it today, I'll try to get to it Wednesday, but blah, blah, blah. Or I'll know where the concerns are. It would be very to your benefit, those of you who have studied at all, to sort of to try to use me to help you along. Okay. And anyway, you get my point. But last thing, the reason I'm saying all that, I don't know why I'm so frantic. Yes, I do. The reason I'm saying all that about, wait. Okay, so first of all, in a moment, I'm going to turn to the practice exam and I'm going to start just from in past experience. I would say, are there any questions? Are there any questions? I will say that maybe I might say, are there any questions, and put them in the chat, but I'm probably going to start with my own idea of which one is the best one to go over at first. And then you can take me in a different direction with your questions. And I do want you to do that, but unless well, actually, I'm going to say this now. I'm going to say a little bit more. I'm going to calm down. I'm going to say a tiny bit more about like cheating. While I'm doing that, if you can multitask, you might want to put in the chat like what questions or what problems you were the most concerned about. It might help me cater to you today on Wednesday. I will say, I think the questions go more or less in order of how we learned the material, and therefore they do sort of go in order of difficulty and complexity. So, I mean, it wouldn't surprise me at all if you're not up to the last one, or you just automatically are most scared by the last one or something like that. Like I get that, but particularly if someone's like, yeah, I got up to question 2, but right in the middle, all of a sudden, like I was confused, but it would be good for me to hear that in the chat. I am probably, even with whatever you put in the chat, going to start with one particular problem that I think is most worth discussing to get the ball rolling, but put anything you want in the chat, and please trust that that information will be valuable, even if I don't get to it right away. And please notice almost every one of those problems is labeled with what problem we studied in homework or in lab that it's most similar to. Like, you should use that as part of your, I mean, I hope it speaks for itself, but it's not a coincidence. The more you can even see, even if you're confused by a given problem, the more you can see how one version of a problem is really the same physics as another version of the problem, even if you're still struggling with the physics. But if you can see how that problem with the Wile E. Coyote and the Roadrunner or whatever, really is big old duck, only it's turned on its side. Okay, so side note, right? Like what's that wily roadrunner problem may not look at all like it doesn't involve a duck. It doesn't even involve up and down. It involves side to side or so, or maybe I have a bet. But if you really look at what's going on in the physics and what equations you use when, really, it is just the big old duck problem turned on its side. It's the big old duck problem with a horizontal acceleration rather than a vertical one or something to that effect. I can't even remember. And if you can even see that, you're progressing and you're seeing the physics almost. Okay, I'm going to go over a particular problem in a moment, but one last thing about cheating. Oh, sorry. No problem, direct chat person. Got it. Oh yeah, I think you even warned me of that, direct chat person. You're good. Thank you. Or maybe that was last week, but yeah. One thing about cheating, and this also, if you have any questions about what I'm going to say, what I'm about to say, you should text me or whatever. I have to have a Zoom meeting this week. 2 people that were caught cheating, were allegedly cheating in another. Well, they admitted that they were cheating in another class, totally different class, nothing to do with you guys. Okay, and not, I mean, honestly, not even in the major. Like, no, not you guys, but I have another instructor. I have to have a meeting about that. There are going to be consequences about that. It's like not going to be pleasant for them or for me. It's not something I look forward to doing. I do it. I have Zoom meetings like this or almost every semester at this point with someone somewhere. I hate it, but as you know, it happens at John Jay all the time. It also does happen in my class. I want to be very clear right now. There's a lot on my exams that you're used to consider cheating that I don't consider cheating. I'm explicitly telling you that working with each other to prepare for to do this exam is not cheating. I'm explicitly telling you that going on the web or looking at all your old notes or taking as much time as you want on this exam is not cheating. I'm explicitly giving you about to give you model solutions for the questions that will be on the exam and telling you that's not cheating. I'm basically giving you a draft of the exam in advance. And I'm telling you that you using that draft next to you while you sit down to do your exam is not cheating. And I mean it. It's not cheating in this class in physics. And also, it's not a gift. I mean, maybe it's not a gift. It's not a guaranteed A. And it's not because like I'm a sucker or I just want to pass you along without learning physics. All that stuff is not cheating. And largely it's not cheating because I'm saying that all of you are allowed to do it. So none of you can get a secret or unfair advantage over any of the others of you. So basically people that don't follow rules or don't respect their colleagues won't get an advantage over people that do respect their colleagues. Okay. Like, and I seriously mean that. I want to be clear though, before we go any further, that doesn't mean that I don't think that it doesn't mean that I'm for cheating, or it doesn't mean that I'm for unethical behavior. It means that what the standard of cheating here is it means that if you do cheat here, it's like actually that much more disappointing and frustrating and has more consequences because we're setting up a situation where really, we hope you don't need to. Okay, and we're setting up a situation where the only way you can cheat here, we're setting up a situation, I'm telling you in advance, that your hope for an A, my hope for your A, is not threatened by the possibility of your neighbor or your brother or your sister or your twin sister getting an A. And I'm telling you that explicitly. It's not true in every class. And it may be okay where in the classes that it's not true. Here, you can get an A, someone can get an A, and it doesn't mean you can't get one. You're not fighting for the same commodity. Therefore, the only concept of cheating is in the end of the day, do you pretend to understand things that you don't actually understand? In the end of the day, what cheating is on this exam is writing things down that you don't understand what they mean by the time you write them down. And your entire goal in this exam is actually to prove to me that you actually understand the things that you're writing down. That's where you put all your effort, all your time, all your care, and frankly, all of your presentation, aesthetic polish. Okay, your goal is not to give me correct physics. I'm giving you the correct physics in advance, and so is the World Wide Web. Your goal is to give me proof that you understand at this point the correct physics. I know I've said it before, but I just want to say it again. The way you would cheat on this exam is you would write things down that in your heart you know don't make sense to you. And I just have to warn you one last time that actually I've been doing this long enough that I actually do know the difference. And that's what I'm going to be looking for when I grade your exam. In many, I'm looking for authenticity above everything else. The 5-step method is designed to force a person, even if they're frightened, even if they're modest, even if they think they don't get anything, but if they follow the 5-step method and just do the things and use their notes in all of this, then they'll find by the end they accidentally understand by the time they've written enough drafts and practiced enough. They won't think that they're getting themselves to understand. They won't think they know what's going on, but then they'll find by the time they're writing a final copy, they actually do get stuff that they didn't think they were going to. That's what you want to do. Just be modest and humble and write down only what you do understand and show me what you do understand. And then even wrong answers or weak links or tenuous grasps, as long as they're totally authentic, you'll find contribute to an A far more than you would have ever recognized. But you'll find that if you write a lot of correct physics that you got somewhere else and it never went through your internal processing unit, like that's what you will find. I have found that's what will get the bad grades, and not because I'm going to bring you to court over it, but because it just will fall on its sword. Okay. Anyway, not to scare anybody, and similarly, if the time comes that the exam gets posted and the time for the exam, the one thing, if you're going to have a problem with turning it in on time or coming to class today, you've got to communicate with me in advance. It's okay. All that is just to say, like, I hope this exam is designed so that everybody here can get an A and I can feel good too, but so that everybody can deserve an A. And it works. This weird method works because somehow every semester, some people find a way not to. And that's what you want to avoid, being one of those people. Okay. Well, okay. Sorry. So I'm seeing in the chat. So what I'm saying is, okay, so I see this in the direct chat, and I don't know when it was written. Oh, it was written 6 minutes ago. So maybe the person in the direct chat. So someone in the direct chat is asking, what is considered cheating? Super huge question. So huge. That's actually what I'm taking a moment to try to address right now. It was written 6 minutes ago, so maybe the direct chat person can tell me if I did just address it. What I'm trying on the Zoom, the board just went away again. What I'm trying to tell you that what the ultimate standard of cheating in this class is if you write things down that you don't actually understand, whether they're right or wrong. It's not cheating to write things down that you got from some other source, that you got from a friend, that you got from Khan Academy, that you got from notes from me. You can get the information from anywhere, as long as by the time you write it, you can show me why it makes sense. But it's oh, you do. Okay, thank you. All right. So, and to everybody, how do you and this is a more subtle measurement of cheating. I mean, it's simpler, but it's harder in a way. But everybody knows in their heart whether they're doing this or not. And the way to know if you're ever insecure, if you just want to do good and do right, but you're taking this so seriously that you're not sure and you're afraid you're going to accidentally do something that might be considered cheating. And because, by the way, we all know that we've all gotten through science a lot of times by writing things down that we don't. I mean, so how do you know? 2 quick ways. One, when in doubt, write more, not less. Every single thing I just fed. That was just so you know, I just fed her.
Oh, okay.
Okay, thank you. Okay. Okay, quickly, and then I'm going to move, and then I'm going to literally physically move, and we'll physically move to the problems. I'm saying this all to encourage you, not to scare you, but to clarify. 2 ways. One, write more, not less. When in doubt, if you figured something out, anything in your brain that you're like, okay, then I divided both sides by 2. Does he really need to know that? Yes. If you can even envision in your mind, like, then I divided both sides by 2, then I crossed out the X's on both sides because I divided both sides by 1. Yes, anything you could even think of as a step, if it even occurs to you to ask, write it down as a step. The more you can divide your thought process into tiny, tiny grains, the more you're showing me that you understand. Sorry, I'm just moving. The other thing is, just in any moment, ask yourself, if Yaverbaum pulled me into a Zoom meeting or pulled me into his office and asked me to explain my work vocally, okay, which is sort of what's happening this week with me and with the two students in another class, okay? If I pulled you into a Zoom meeting and asked you to defend or explain your work vocally, could you do it? I mean, that's really the standard. Can you orally, vocally, however you want to say it, defend the thought process? Okay, so, but when in doubt, but that's also why we're practicing this week. Try on the practice exam to see if you know what I mean. And if you have questions, text me. I'm just moving and we're going to move. Okay, but all that, when all is said and done, anyway, whatever. When all is said and done, I think you'll find with this method that it's a little unusual, but by the end, you'll know that you know what you know in a way that's deeper than sometimes else. Okay. But I'm happy to keep answering questions as we go. I just moved. I want to turn to a problem. I'm going to put the board back. The board I keep losing. I don't know why. But we're going to turn. And again, please tell me in the chat which questions we have today and Wednesday to go over this. And I will be posting things. I really shouldn't be talking so quickly and frantically, but I am. The problem I want to go over right now, if you could turn your attention to, I just lost it, is the one problem that it seems like we never talked about. Where did it go? Oh, here we go. The one problem that is the problem that seems the weirdest in a way. I mean, maybe it is weirdest, is problem. I'll screenshot it. I mean, I'll screen share. It's it's page, okay, it's page 5. I want to go over part 3, Galileo's principle of relativity applied in 1D. I'm going to screen share it. Yeah, this business, okay, and pardon me. All right, so you want to look at what? That is not, no, that's the front. I'm sorry. Try this again. Okay, here, this. Please take this out or get it ready. Or if you haven't thought about it yet, think about it for a minute. In fact, I'm even going to say, if you look at this for a second, I'm even going to say the answer. And then I'm going to give you a chance to think about it for a minute. I'm going to walk away for 1 second to get my head together. But I think all right. I'm going to say, I think the answer is 1.5 miles per hour. That's what I think. 1.5 miles per hour. That the question is asking. Now, I don't think that's easy, but I think it's simple. You'll see there's a very hard way to get that answer, and there's a very straightforward way to get that answer. But what with the question is, what's the speed of the current? I.e., what is the speed of relative to the shore? That's what it's ultimately asking after it gives you all these facts. It's asking how fast is the water going relative to the shore? How fast is the water going in the frame of reference of the shore? How fast would you see the water going if you stood on viewing yourself and the shore as at rest? That's what it's asking, right? And I believe the answer is 1.5 miles per hour. You could think about that and I think there is, well, and I'm going to walk away for 1 second, but I think that, of course, I'm going to go over it, but I think that's the answer. Hang on. Okay. I'd be curious. So I'm going to explain now. The reason I want to go over this problem that's on the screen right now, and I will switch my board and I think The reason I'm going over it, it may look the least like any problem we've done. I mean, I think it does look the least like any explicit problem we've done. This is totally about a concept, about the concept that I think underlies this whole exam. The concept of Galileo's principle of relativity. We first saw it in the train of thought experiment homework. We've seen it in different forms. You should know all the different forms. You don't have to memorize them because, again, this is an open book test and all of that. But this problem is designed to really show you that these seemingly abstract, conceptual, sort of like physical ideas that sound like philosophy and don't really sound like science, or they don't really sound like they do anything for you in mathematical problem solving. My argument is, no, my argument for this whole exam and for everything in physics is that, like, people always know how to do the mathematical computations in a physics problem, and not always, but often, even if they're afraid of the math, it turns out the math is always the part that they're comfortable doing. What people tend to be nervous about or frustrated by is how you set up physics problems, how you start them, how you get the math going. Once the math computations are going, people are often okay. But what math to set up is the challenge to a lot of people, which really is to say that what's challenging about physics isn't the math, it's the physics. And what I think is that the missing piece, the piece that gets a lot of problems going, but you have to get used to that, is Galileo's principle of relativity. It shows you how to set up math and then, or how to set up math in the most convenient, easy way possible. And once you use the principle to set up the math, then the math takes care of itself. So put another way, this is an example where that principle that all velocities are relations between pairs of objects, not properties of single objects. I believe this problem is a classic example of showing where, if you really believe that and get it, the math is straightforward. I'm going to show you. But if you don't believe that, or don't get that, or don't use that, and you just try to churn through a whole bunch of equations, you can get this answer. You can get the answer I just said, but it takes a much longer time, and it gets very hairy if you don't take seriously Galileo's principle. Now, I'm going to explain how to do it, like, my way. But the reason this is in the exam, I think if you follow what I say, I think it helps with all the other problems in the exams. I'm going to start doing it in a minute. I would be very interested if anybody has the guts, and you'll get points and all that. If anybody in the chat could even, I'm going to pause for a second, even tell me if you even tried this problem. You don't have to tell me the answer you got. I'm not trying to embarrass anybody or make anybody nervous. But if you could tell me in the chat if you even did get an answer, certainly if anybody did get the answer I just said, I'd be delighted to know that. Also, if all of you got the answer, it's not, then I should move on to something else. But just tell me in the chat if you even tried this, if you even got an answer, or if you got stuck, or so, just give me some feedback, basically, so I know who I'm talking to. I mean, if if I don't see anything in the chat, I'm going to assume that no one's gotten that anything I say about this problem is beneficial to everybody. Okay, something is in the chat. That's a good thing. Okay, that is honest. Thank you. One person director. I appreciate the honesty. And I'm going to, there's two people. Oh, a bunch of people. Oh my God. Wait, wow. Okay. No, this is honest and it's good. It means what I'm not. Okay, good. Okay, fine. There's like 5 people in the direct chat. I'm not going to say them by name, but all you people that just put in the direct chat, okay, at least you're making me feel like I'm not going to waste your time by talking about it. Okay, so cool. Okay, so I'm going to go. Okay, and just remember when. Okay, all right. Okay, hold on. So I'm going to switch boards. We're good. Thank you. I appreciate that. So, all right, I'm going to start with the diagram. So here's the diagram. So here's the deal. Here's this bridge. The bridge is basically like y naught equals 0. I mean, that's like the origin of the coordinate system. I'm making a coordinate system here, as I should do in every problem. I'm going to call the upstream. So the river is flowing downstream. I mean, by definition, that's the direction of the river. So I'm going to call up positive. I'm going to call down negative if necessary. This is a bridge. So basically, this is just the same diagram as what's given. But what we find is that a boat is going up against the current of some water, right? As soon as it passes a bridge, it drops a bottle. All right, so the experiment begins when so the bridge just is a reference point in space and time where a boat, it's traveling upstream at some speed, sorry. Okay. We know that this boat is going up against the current of the water. It passes a reference point, a bridge, which we could call y equals 0 or something like that. When the boat passes the bridge, it drops a bottle off the boat. It keeps going for 20 minutes and then realizes, oh no, we dropped a bottle off of our boat. So after it's gone upstream 20 minutes from the bridge, and again, the bridge is just like the way the whole experiment starts, just where we started our stopwatches and started paying attention. When the boat is 20 minutes above that, it realizes it dropped the bottle, so it turns around and starts coming back to the bridge. Now, this whole time, the bottle has continued to sit in the water and float downstream. It's continued to float downstream while the boat has been going upstream and then turning around and going back down again. The bottle has continued to go downstream. So by the time the boat gets back to the bridge, the bottle is way below the bridge. It's not there anymore. It's been floating down. And stop me if you don't understand that or you don't like that. But the boat is paddling in the water. In fact, let me back up and say that the problem says explicitly the boat has been paddling up the water at some speed, like it's going up because someone's paddling. It's going at some speed, VBW, some speed of boat relative to water. It has some velocity. The absolute value, the magnitude of that velocity vector is speed. The speed up of the boat relative to the water apparently stays constant throughout this entire experiment, stays so constant that even when the boat turns around and starts going down, it continues to go at the same speed relative to the water as it was before when it was going up. And that's not, I mean, that's a super important fact, but it's not meant to be a confusing or unnatural fact. It basically just means everybody's paddling at the same rate. Like their arm muscles are doing the same thing, right? So the speed of the boat relative to the water means whatever speed, it means the speed you would observe if you were a lily pad or a bottle just floating in the water watching this boat. you would see the boat going one way at some speed, and then later on, you would see it going the other way at a different speed. But if you're in the water watching the boat, you would never see that speed change, only the direction. And again, that's realistic and fine. Like that just means that people are pushing the water away from the boat, like with the same strength, the entire duration. Okay. Therefore, I'm over explaining this as always, but therefore, the bottle starts coming downstream once it realizes the boat starts coming downstream once it realizes that it's missing a bottle. And now, because it's like somebody walking down a down escalator. It's going to pass people who are just standing on the escalator. I hope that's clear. And it's certainly going to pass people that are just standing in the subway station, right? The boat was going up a down escalator in effect until it realized that it dropped a bottle. Now it starts going down the down escalator and it's trying to catch up with something it dropped on the escalator. So eventually it catches up with that thing because that thing has just been sitting, right? Just sitting in the water. Eventually it catches up with that bottle. It doesn't catch up with it at the bridge because that's where it dropped it. And the bottle continued to go down since the drop. But it does catch up with it somewhere below the bridge. How far below the bridge? We're told 1 mile. Okay, this is the setup. We've got 3 objects here. We've got boat, water, and shore. We're told 20 minutes to go up, and then we're told 20 minutes until the discovery point, and then we're told 1 mile from the bridge to the reunited point below the bridge. Those are the 2 time-space facts that we're told. And the one other super important point that we're told is that we're not told how fast the boat is going relative to the water, but we are told that whatever that speed is the same no matter whether the boat is going upstream or downstream. Let me also point out, we are never told how fast, we're certainly not told how fast the boat is going relative to the shore. And I'll just say, God, I'm getting myself, these are the facts that we're told. But the 20 minutes and the 1 mile are 2 facts. But another fact is that however you want to write it in your own notation, VBW up, magnitude thereof is equal to VBW down, magnitude thereof. Those are the 3 facts. Now the question, and please stop me, the question is, so that was all step 1, DFP. The question is, given all the above, the question is, we know we know something about VBW. We don't know the number, but we know something about it. We in effect know that VBW is the same up as down. What we're being asked is what's VWS? No, so okay, that's our question. Like, what's the current given all of this? It seems like a very hard question. I'm going to pause for a sec. Sorry, I know I'm. Oh, chat. There's something in the chat. That's good. Oh, good. Oh, thank you. Actually, I really needed that this time, Nicholas. Okay, thank you. I was okay. Because I was going to say, please put in the chat even if you don't know how to do the question now, and there are more than one ways to do this question. I'm going to show you the most straightforward way to make a point. But can I just get, all right, sorry. Can I just get a show of hands? I'm changing the view. Do you, even if, and I understand a lot of people didn't look at it yet before now. I totally get that. Can you raise your hand if you think, looking at it now, do you understand what the question is asking for? Thank you, Savannah. Thank you. Okay, awesome. Oh, thank you. I love this class. I'm going to miss you so much, but you're not going anywhere. Yes. Okay, cool. All right. So that's what it's asking for. Now, if I were taking this test or taking this practice right now, okay, and this is, well, I've done step 1, I've done step 2, right? That was step 2. What is the question? Step 2. So one thing I would definitely write down for step 3 for GDP, like how do I even begin this? One thing is, this is clearly a question about the relational character of velocities. This is about how, let me put it this way. we're ultimately being asked to know how fast the river is going relative to the shore. One thing that makes this mysterious or intimidating is just like our early problem with something going up a hill and down a hill. One basic fact that we seem to be missing is how fast is this boat going? How fast is the boat going relative to the shore? Like if I were standing on the shore and just watching all this, I would have a much better idea of what was going on. And I hope it's clear. Well, anyway, here's what I'm trying to say. The principle here is, one way of putting it is, we know velocity of boat relative to shore equal, or we can even say, if you want to practice for this exam, I know as a principle, Galileo's principle says that given any three objects, I'm writing this fast, you should write this a little bit more carefully, but given any three objects, A, B, and C, we know that velocity of A relative to C equals the velocity of A relative to B plus the velocity of B relative to C. Or in other words, in this, right? So in this case, right, in this case, just to be clear of what I was saying last week and stuff, we have three frames of references here, three objects, all going at three different velocities. We've got a shore going at one velocity. We've got a water going at a different velocity. We've got a boat going at a different velocity. They're all different. Each one of them in its own frame of reference can say, I'm going at rest and I'm looking at the other two. Like for sure, if you're standing on the shore is attached to earth, you could say, I'm still, and I'm watching a water go by me, and I'm watching a boat go past the water. Just like if you're in Columbus Circle Station, you can look at an escalator and say, I'm sitting still, the escalator's moving, and then you watch someone walking on the escalator and you say, and that person's moving relative to the escalator. You can certainly say that and do a bunch of physics and it would all be valid. But just to be super clear, someone standing on the escalator can just as easily look at the station, say the station's going past me, and a person next to me is going past me in the opposite direction. Like every single reference frame can view itself as at rest, play its own little video game, watch everything else go past it, right? And the key point here is that each one of those reference frames is equally legitimate, equally valid. That's the physics hook. The Earth can look at the sun and say the sun's going by, or the sun can look at the Earth and say the Earth's going by. They're both correct, and they're all correct here. So so I say all of these three have three different velocities. If you say which is the actual one that's at rest, there's no answer to that and no need for an answer to that. But each one of these can view as itself as at rest, and therefore each other one can view its velocity as a combination of the other two, like the boat going on the shore. So these are just examples of way I can assign A, B, and C. As long as the pattern of the letters is the right pattern, there's a number of different ways I can write how these velocities interrelate, such as the boat relative to the shore is definitely the boat relative to the water plus the water relative to the shore. That's our standard. That's like the escalator train idea. Or I could say the water relative to the shore, which is what I'm looking for. I could say the water relative to the shore is the water relative to the boat plus the boat relative to the shore, right? And don't forget, and anything that works, if it works, it works. And don't forget, if you're like, wait, water relative to boat, what do you mean water relative to boat? I thought, like, you might look at one of these or say, or you might say, yeah, you might say water relative to boat, but the boat's moving. Why is the boat a frame of reference? The boat is its own frame of reference. Remember that that anything to itself is zero, right? Anything to itself is zero, and the water relative to the boat, by definition, would equal the opposite of the boat relative to the water. These are all forms of Galileo's principle of relativity, and they're all mathematically helpful, right? It's our what we have to decide is like which one is the most helpful here. But the key thing about all this, so I would write this down as a step 3 GDP, some versions of these that help me isolate what I'm looking for. What I'm ultimately looking for is the water relative to the shore. That's the current. That's what I'm looking for, right? Now check this out. Here we go. If you really believe, now again, there's a bunch of different ways to do this. I can make the math very complicated if I want to, or if I'm not careful. But if I really believe this principle, I'm going to the next page. So I'm still in GDP according, and this is where it gets physics, not math. According to GPR, Galileo's principle, the laws of physics, right, are the same in each of these reference frames. Like the laws of physics hold for the water, for the boat, and for the shore, all the same. So I can do physics from any perspective I want. Therefore, but I have to choose a perspective. So I can choose any perspective I want. So I'm going to take advantage of the principle and choose the perspective that is the most mathematically convenient. It might not be the most obvious or the most natural, but I'm going to choose the one that's most mathematically convenient. That is what I'm going to do is this. For convenience, or to maximize convenience, let's solve in or from, whichever you like, the reference frame the perspective of the water. I'm going to look at this problem from the perspective of the water, which is the same thing as the bottle. Let me pause on that for 1 second. Remember, the bottle is just floating in the water. Remember that a reference frame is not a location. It's not a place. It's a perspective. It's a coordinate system. It's defined by motion. That is to say, anything in the world that's going the same speed and direction as the water is in the reference frame of the water. Anything in the world that would see the water as stationary and see everything else as moving is in the perspective of the water. The bottle is just floating in the water, right? Like the bottle would look to its left and see some lily pad, you know, or some like water molecule there. It would stay with that water molecule the whole time. It would never see the water molecule move at any velocity. And similarly, a water molecule to the left of the bottle would look at the bottle and it would never see the bottle like receding or zooming away from it. They're in the same reference frame. So I'm going to look at this problem from that perspective. I'm going to say that the bottle is stationary. The bottle and the water are stationary, and they're seeing stuff happen from the bottle, water, frame of reference, reference frame, coordinate system, perspective, all the same thing. right? If you're that bottle, from the moment we say go, the bridge, if you're that bottle in the water, what do you see? From the moment you're dropped, you see a bridge going up like this away from you, right? You see the shore, the bridge is attached to the whole shore. You see the shore going up away from you, upstream, right? At the same time, you see a boat also going up away from you at a much higher speed, at a higher speed than the bridge. Please try to picture that in your mind and tell me if you can't picture that. But if you were the bottle, you would see a bridge going up like this. You would see a boat going a lot faster, going up. At a certain point, you'd see the boat turn around and come back to you while the bridge kept going just the whole time, right? Like, because if you were standing on the bridge, you would see a bottle going down the entire time. So if you're the bottle, you see the bridge going up the entire time. While the bridge is going up, you see a boat going up and then down, right? Stop me if you don't buy that. So I'm watching it from the perspective of the bottle. From the bottle, from this perspective, the boat goes up for 20 minutes, right? It goes up for 20 minutes. Now, check this out. It then realizes that it dropped the bottle and starts coming back to the bottle. You're the bottle. Now, this is the most important part of this whole thing. If you're still with me, the thing I'm about to say, it's the most obvious and the most confusing at the same time. If you're the bottle, you see this boat going away for you for 20 minutes. It travels a certain distance, which we don't know because we don't know how fast it's going, right? We don't know how fast the boat is going relative to the water. We don't know, but we know it travels for 20 minutes, some unknown distance. Right? But then the bottle turns around. I'm sorry, the boat turns around. Comes back to us. To us. Us is the bottle. Now here's the part. The boat turns around and comes back to us. It went up an unknown distance for 20 minutes. It's now going to come back to us. Well, it's going to come back to us the same unknown distance. Pause on that for a second. This is the key. This is physics, not math. I'm going to say this again. I'm going to say it a couple different ways. The boat goes up a certain distance, some unknown, the same unknown distance relative to us, the bottle, relative to us, the bottle. I'm saying the boat went away from the bottle, went up for 20 minutes. Now it turns around and starts coming back down. It's going to come back down the same distance as it went up, the same distance relative to us, the bottle. Now, I don't mean it's the same distance as measured by somebody who's standing on the shore. This is super important, and this is the whole nub of the physics of the problem. So if you're following this scenario, if you are standing on the shore watching all this, if you didn't know anything about physics or different perspective, or blah, 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 and you're standing on the shore and you watch the boat go up and then come down to meet a bottle, for sure, on the shore, I'll even try to draw this. What the shore would see, something like this, it would go up a certain amount and then come down a longer amount. That's what right? If you were standing on the shore, you would see the boat go up above the bridge some amount, 20 minutes, and then the boat would come down to the bridge and then keep going and reunite with the bottle. If you're standing on the shore, you see the up trip short and the down trip long. If you're standing on the shore, and I don't care where you are. I mean, if you're not traveling with the water, that's what you would see. But the bottle would not see that, would not observe that, and the bottle would not be wrong. The bottle would see this. Same. The bottle, because the bottle is in the water, or put another way, a water molecule would see a boat separate from it, and then a boat come back to it. It is not moving. It's seeing a shore move past it. It's seeing a bridge go up past it the whole time, right? So picture yourself standing on an escalator in Columbus Circle or in a subway or whatever, right? You see the world go by you. You don't see you moving. And this is not a trick. This is like any measurements you would do. And again, this is like, or you're standing on Earth. You don't think of yourself as moving, but half of your brain believes you're going at 65,000 miles an hour past the sun, right? So I'm saying, picture yourself in this water. You would see a boat go away from you, and then the boat comes back to you. Anything in life that goes away from you and then comes back to you went away a certain distance and then comes back that same distance. It can't be a different distance. If it goes away from you and then comes back to you, from your perspective, it went out a certain distance. This is key. There's going to be one more key to this, but I want you to ask yourself, I see the time. Pause for a second. You'll know you're with me so far if you see how, from the shore's perspective, the boat goes, like from the shore's perspective, it goes up a certain way and then comes down a much farther way. But from the water's perspective, and this is why I'm choosing the water's perspective, because it's going to make my life a lot easier. From the water's perspective, I see a boat going up and then coming back. From a water molecule, from the bottle's perspective, I see a boat separate, run away from me, and then come back to me. So it goes away a certain amount, it comes back that certain amount, because I'm just me. I'm just sitting around. Am I actually moving? No, nothing is actually moving. Is the shore moving past me while this is happening? Yes. But do I care? Does that have anything to do with the boat at this moment? No. So, or in this way of thinking, no. So the boat goes away from me and comes back. Now, why am I making such a big, hold on, I'm going to pause again. I know it's 1:13. I've got to ask this. Do you, well, no, I'm going to keep going. I'm going to ask for check-in a second, because there's one more statement. Now, if you're really with me, I'm saying now, from the bottle's perspective, the boat makes a round trip, literally a round trip. It goes out some known amount, comes back some known amount. But now here's the key, or the second key. Thus, but we said, here's the other key fact in the problem. But, well, the other key fact in the problem is W up is the same, we said, well, not is the same, we said, as VBW down, right? So if that means the speed of the boat relative to the water is the same, whether it's going up or down. Now, again, if you're following this, that's not true of the speed of the boat relative to the shore. It can't be, because of what I wrote 2 pages ago. Like, for sure, if you've ever boated on water, if you've ever walked up or down an escalator in Columbus Circle, like, you know, when the boat was going up, from the shore's perspective, it was going very slowly because it's trying to go up relative to the water, but the water's coming down. So there's like a minus sign involved. It's like walking up the down escalator. You don't progress that effectively compared to the subway station. But then when the boat was coming down, it's going down, it's going to some speed relative to the water, and the water is going to some speed relative to the shore. So they like add together, and it's going really fast on the way down from the perspective of the shore. But and that's why the shore is a difficult perspective. In the shore, the two distances are different, up and down, and the two speeds up and down are different. So the shore perspective is the natural one, sort of the obvious one, that if we didn't think about physics, we might imagine is even the true one. But the shore one is not any more true than the water perspective, and it's definitely not as easy, because in the water perspective, now I'm going to say the distance on the way out was the same as the distance on the way in, and I'm now reminding myself the one other given fact in the problem: the speed of the boat relative to the water on the way out, on the way up, is the same relative to the water as on the way back. So if it went a given distance out and then came the same distance back, but it did both at the same speeds, then both times must be the same. Like here, this is the second thing really worth thinking about in this problem, the second physical fact that no number of computations will allow you to see as much as just physics will. Therefore, since up, speed, and distance are the same as down, speed, and distance, since the speed and the distance for the up trip are the same as the speed and the distance for the down trip, the time up must equal the time down. So I am saying that if the boat and the bottle were separated for 20 minutes while the boat went upstream, then they must be separated for exactly 20 minutes while the boat is coming back downstream. I'm not saying the problem said that. I'm saying it follows from all the facts in the problem. I'm saying it's actually the insight, it's the revelation. I'm saying that boat trip back down to bottle must take 20 minutes. I'm saying T up equals T down, which both equal 20 minutes. I'm saying I just figured that out, and I'm almost done with the problem now with 13 minutes left. I just figured that out. Again, I'm saying the problem didn't say that. The problem just said up is 20 minutes. But I'm saying if you really think this through from the perspective of the water, the up trip and the down trip must both take 20 minutes. Now, again, if you're looking from the perspective of, that's not obvious, because if you're looking from the perspective of the shore, this 20-minute down trip I'm talking about is the 20-minute down trip that takes all the way from above the bridge all the way to down below the bridge. It's a longer trip from the perspective of the shore. So it wouldn't have occurred to me that it would also be 20 minutes. But from the perspective of the shore, it's also a faster trip. Because from the perspective of the shore, BW plus WS equals BS. Like, from the perspective of the shore, we have a down trip that's longer in distance and faster in speed, therefore same time. But from the perspective of the water, we have the water is the easiest way to look at this. It's the whole point of the problem is if you really believe in relativity, look at this from the perspective of the water. And now we're just about done. But if you believe, and I'm going to stop. Oh, okay. I'm going to stop. From the perspective of the water, we see a boat go up 20 minutes, come down 20 minutes. That's from the perspective of the water, i.e. total trip, i.e. total time, total round trip time, if you like. Sorry, total round trip time equals 40 minutes. Again, I would not know that without having figured it out. But it equals 40 minutes. Now, therefore, so what? Well, therefore, like, so what? Well, during that time, during the 40 minutes, during this time, if I'm a bottle, right? Or if I'm a water molecule, if I'm a bottle, during this time, what about the whole shore? Well, during this time, the shore has been going up the entire time, like the bridge has been going up the entire time, right? From my perspective as a bottle, I've watched a boat go 20 minutes, 20 minutes, and come back to me. Thank you, bottle. Like it ran away, it came back. I'm just a piece of water. I'm just a bottle in the water. I'm just watching as a boat runs away, come back. Now, meanwhile, if I looked over here, though, the whole time there's this bridge, like there's, you know, the bridge and the shore and the woods and the trees and everything attached to that. They're all going past me. Just like when you're on a train, you're sitting still, you watch the platforms and the other subway stations in the New York City streets all go past you, right? So if I'm the water, this entire time I've watched a bridge go away from me up, right? And what? It's gone away from me up for 40 minutes. According to the original diagram, there's one other fact given in the problem that I've not yet used. I've used every single fact in the problem so far, except this one fact, which says in the diagram that when the boat and the bottle reunite, they are 1 mile below the bridge. From the bottle's perspective, that means when they reunite, the bridge is 1 mile above them, right? like from the bottle's perspective, boat went and came back to me. And the moment it came back to me, I look up and there's the bridge a mile above me from my perspective, right? So during 40 minutes, the bridge, the shore, has traveled 1 mile above, like above me, us. Us means the bottle, water, frame of reference, right? So from the bottles, from the water frame of reference, therefore the shore relative to the water, right? The shore relative to the water seems to equal the velocity of the shore relative to the water equals positive, because it was going up, 1 mile in 40 minutes, or which is a perfectly valid number, but put another way, 1 mile in, if you want this in miles per hour, in 2/3 of an hour. So that equals 3/2 mile per hour. And so then technically, if that's VSW is positive 3/2 miles per hour, then technically VWS equals negative of VSW. VWS equals negative 1.5 miles per hour, 1.5 miles per hour, i.e. the water. So the negative just means down, according to my initial coordinate system. The water travels down past the shore or the bridge at 1.5 miles per hour. Now I'm going to pause for a second. Like, this is the answer. Now I'm going to say, I've got 7 minutes left. I'm going to pause for, I want you to think about it. I'm going to say right now, it's not the most complicated problem in the whole exam. There are definitely exams with a lot more computations to be done, for sure. Well, although I think all those other ones have computations that are very much modeled by computations we've already done together, like on Zoom and stuff. And I will post many of the other computations, and we'll do more of them on Wednesday, maybe more obviously your choice. I mean, maybe we'll make sure that they're more like your choice of computations. The reason I just went over this problem right now, okay, on purpose, is that this one has the fewest computations in a way, but it's the most physics thinking of all of them. This one is an example, like I just got an answer for you. And again, I'm going to pause. We're going to have 6 minutes for questions or whatever. But I just did it for you. For sure, when you get it on your this will be on your exam. I will change the numbers just enough so that you can't just like literally copy this, or I'll change some, probably just the numbers. Okay. This is one that you want to practice, like drafting your own response with your own diagrams. You'll also see that my diagrams were kind of messy and gross. My handwriting was gross. Like, this is a perfect example where you know in your hearts whether you get right now what I just explained. I would hope that most of you, if you're just paying attention, I would hope that honestly that most of you are like, I kind of get it, but whoa, that's weird. Wait, I'm not sure I totally get it. Or I think I get it, but I don't even get, like, you might even be thinking something like, wait, but okay, but that's only the answer from the perspective of the water. What, I mean, what if I did want to do it from the perspective of the shore? Like, could I, or would I get the same answer? Or is that really, it seems like what he just did was a trick. Is it really actually fair? I don't, you might have all, you want to think about this. If you're just sitting there right now going like, yeah, duh, obviously, of course I could do that. Then I think you better practice and you better see that it is conceptually physics for real. If you're a little bit unsure, but you kind of get what I just said, you're probably in exactly the right position. But you will know. There's like for example, there's 2 moves in here. When I said that the up distance is the same as the down distance, and said the up speed is the same as the down speed, therefore the up speed is the up time is the same as the down time. I want to stress again, that is not obvious. If you just think like, oh, duh, yeah, okay, I could do that. That is only obvious in the frame of reference of the water. The trick of this or the technique of this problem is trusting yourself to pick a frame of reference that isn't planet Earth. This is a perfect example of a problem, going back to someone's direct chat question, where this one, when you try to write this up your way, you will know, and I will know, if you've just literally copied the numbers from my sheet and just turned it into an algorithm, or whether you get what's going on conceptually. And if you get what's going on conceptually, your presentation, frankly, is going to look a lot prettier and clearer and more personal than mine. And also, if you get what's going on here, you're actually going to do much better on the other problems in the exam. I would practice this one first in a way, if I were you, like practice writing it out your way, or explaining it to a friend who wasn't here today or whatever. Like, this one is physics. It's not just copying computations. Okay, enough. No, wait, we've got 3 minutes. What letter? Oh, okay. So I see someone in direct chat. What we just saw, I'm going to switch the screens. What we just solved for. Okay, oh, good. I am getting some questions in the chat. Okay, we got 3 minutes. So hold on. I'm going to try and go to order. First of all, what question did we solve for? We did part 3. Well, I'll screen share. Hold on. Sorry. And obviously I'll post these notes as always. This is what we just solved for, this one here. And you notice there's only one question. Page 5 is what we just did, page 5. And there's only one question on page 5 too. It's like very open-ended. I mean, I don't know what to say, but it's page 5 is what we just did. And there's only one question on it. And that's the answer that we solved. We got the speed at which the water flows relative to shore. We got WS. Okay, that's one question in the direct chat. But now another question in the direct chat. I'm going to try, and also we could pick up on this on Wednesday. But why it's 1.5 miles? It's 1.5. So someone said, I'm still confused why it's 1.5 miles from the shore's point of view. Oh, in other words, okay. So it's 1.5 miles per hour. Excuse me. It's 1.5 miles per hour of motion from the shore's point of view, because, and there's a fast answer, maybe I need to give a longer answer on Wednesday. I mean, you might want to think through the whole question to see that, but if you're asking, why is it 1.5 miles per hour from the shore's point of view? I think what this person is quite reasonably asking is, okay, I kind of see how you got 1.5 miles per hour as an answer the way you were doing it, but how is that actually the answer, like from the shore's point of view? And here, like, because you, Yaverbaum, were doing it from the water's point of view. And isn't the question asking how fast is the water going past the shore? Yes, it is. But if you look at my calculations, what I actually got in the end is I got what the shore was doing relative to the water. That's what I got. I got how fast the shore was going relative to the water. I found that if I'm the water, I see the shore going up at 1.5 miles per hour. But that means, by Galileo's principle of relativity, if the shore is going 1.5 miles per hour up relative to water, then water is going 1.5 miles per hour down relative to shore. It's like if the Earth is going 65,000 miles an hour to the east, to the west relative to the sun, to the east relative to the sun, then the sun is going 65,000 miles per hour west relative to Earth. So I got shore relative to water. That's how I solved on purpose. But then at the end, I said, okay, fine. Then the answer we're looking for, water relative to shore, is just the negative of that. Okay. Okay. Sorry. Okay. How did I get the number? Okay, it does. So I am running a little bit out. Here's the deal. So the person in the direct chat actually met the number. Where I got the number 1.5 was, the key is that this entire everybody bear with me for just, I mean, if you have to go. But if this is helping anybody, just hang on for a second. I know it's 1:30, but a person's asking, like, where did I get that number from? Numerically, here's how. This entire experiment took 40 minutes, 20 minutes for the boat to go up. And then I did a lot of thought that you may want to also do to realize that if it took 20 minutes to go up, it therefore also took 20 minutes to come down. It took the boats and bottles separated for 20 minutes, but then they took 20 minutes to reunite. I had to think about that. You have to think about that, and we can go over it again on Wednesday, but it's 20 minutes out, 20 minutes back. So that's 40 minutes, a total of 40 minutes. But during that 40-minute time, the problem says that the bottle ended up a mile below the bridge. that means that during the entire experiment, the bridge went up a mile from the bottle. I mean, put it either way you want. I'm saying what we figured out, the key that we figured out was that it was 20 minutes down. Therefore, 20 minutes up, 20 minutes down, that makes 40 minutes. But the entire motion was 1 mile in 40 minutes. So that's 1 mile in 2/3 of an hour. It's like 1/2. Therefore, that's the same as 3/2. What 1/2 is 3/2, 1.5. That, oh, okay. I don't know if that, okay. I know we have to go, but please look at other pieces in the practice exam and ask me on Wednesday. We'll keep doing this Wednesday, but you can go. I'm gonna hang out for one more second. So the person who just asked me about the number, did I answer? But you can go, guys. Sorry. I'm just gonna hang out for a second to make sure we did that. Oh, thank
Thank
you.
you.
Good day, Professor.
Thank you, Professor. Have a great day.
Thank you. Thank you. And this stuff. But direct chat. Oh, was that direct chat person? Oh yeah. Oh, okay.
So,
Oh,
Professor, so what? I